Hi, this is the control cabinet for my CNC mill. Similar to last video, I will be reviewing my build and working on improving the machine. This time I will go into the wiring and the motion control side of things. In the box there are things you would expect like power supplies, a VFD, motor drivers, and a control system running Linux CNC. Right now the control setup is an all-in-one PC and a simple analog breakout board, but I will be replacing it with this, a Flexi-HAL CNC controller. And while doing this, a bit of reorganization and much needed cleanup within the enclosure. I initially went for a breakout board for its simplicity and low cost, but after encountering a few issues and limitations, I wanted to upgrade. So this is also what I want to go over. Before I go into the whys and hows, I want to quickly explain what I'm talking about. The CNC controller or PC receives G-code, which is essentially a list of instructions written in a specified language. This list of commands then needs to be translated into actual movements of the stepper or servo motors. I'm skipping over a lot of details, but essentially we did a system that knows the machine's capabilities, keeps track of its current position, and monitors everything. This motion controller is responsible for converting G-code into motor commands and the trajectory planning. So the system will basically convert the G-code into specific instructions like X2 needs to move this many steps, Y that many, and it should be done at that speed. This information then needs to be sent to the motor driver, which controls the stepper by switching the polarity of the coils. In my case, the controller wants a high-low value for direction and a pulse to go a set amount. So we also need a system that then modifies the input-output pins accordingly to send this information to the motor driver. I will call this the I/O manipulation or I/O control. In the case of the breakout board setup, both machine management and input-output manipulation are handled by the computer. The breakout board then mainly routes the I/O signals to the desired places while providing some electrical isolation. Nowadays, legacy connectors like the parallel port are uncommon and mostly older PCs still have native support for this style of connector. However, PCI adapters like this one are available. The most common legacy connector used is the 25-pin parallel port. Quite a few of them are ground pins, so there are a limited number of quote-unquote useful pins. This is where the I/O limitation of this style of setup comes from. Moving to more advanced systems, the task of interpreting G-code and generating pulses for the motor driver is split up between two components. One part handles the general machine management, and the other deals with the I/O manipulation. By splitting the tasks, we eliminate the need for a legacy parallel port. Instead, digital communication protocols like SPI, Ethernet, or EtherCAT are used. These boards here are just examples. I recommend checking out the Linux C documentation for a full list of supported boards. The more modern approach also removes the inherent I/O limitations of the parallel port and allows us to use much more advanced inputs like encoders for precise feedback next to the basic ones such as limit switches. There is much more to discuss, such as the improved speed and real-time computing performance, but I won't really dive into that. Also because with these type of more advanced systems, the possibilities are almost limitless in terms of features and complexity. However, this does not mean there are no practical or affordable systems available. This is also because Linux CNC supports the use of hybrid systems, combining both legacy analog boards and more modern digital interfaces. In the current setup, all of the I/O is done here on the side, most with these screw tie terminals. Power comes on here at the bottom and then has to go through an E-stop as well as a main contacting switch. This one disconnects and connects both phase and neutral. There's also an additional momentary switch to power on and off the motor driver power supply separately, as well as a Linux CNC halt E-stop. Next to that is a spindle enable override and some basic switches for pumps and lights. Within the enclosure, the power gets distributed to the PC power supply, the motor driver, and an auxiliary power supply, as well as the VFD. For the VFD, I'm using a second-hand Toshiba VFS9 1.5 kilowatt unit. The motor drivers are generic DM556 ones. I also tried their analog counterpart, the DB6600, but I can't really recommend those. The motherboard sits here on the top, connected to the storage, as well as the parallel port breakout board. My main reason for choosing a breakout board setup in the beginning was the simplicity and relatively low cost. I got this motherboard in a computer with power supply and storage for about 35 euros. The breakout board is around 10 and then you add some for cables. So with 50 euros you have a system up and running. Setting up in Linux CNC is also pretty straightforward. Using the step config tool, you can easily configure your machine's axes and switches, and you're ready to go. The wiring is intuitive as well. You can use the basic layout and directly connect your motor drivers, limit switches, and other components. That said, there are some limitations to this setup. Not all motherboards work with the breakout board like you need them to. For example, with an older board, I got the outputs to work just fine, but the inputs just didn't work correctly. Additionally, the I/O is limited, and some breakout boards may have components of them with questionable quality, so this is something to be aware of. The challenge is that these standard motherboards are not really made to operate in the somewhat harsh conditions of a CNC. They're sensitive to dust, vibration, and especially electromagnetic noise. With one of the boards that I used, there was always a chance that the PC will automatically restart when I turn on the contactor for the motor drivers. While these issues can be worked around, it's not the most robust system. Overall, I really like the breakout board system and its implementation into Linux CNC, especially for machines that don't require much I/O, and it's a great place to get started. But if you're looking to upgrade, like me, there are a lot of options. I think the most common route is to go with a Mesa card, such as the 7996. While browsing through the supported boards for Linux CNC, I came across something called the Remora software. This tool allows you to use 3D printer control boards with Linux CNC, and I found that really interesting. After reading a bit more, I found this board, the Flexi-HAL from Expardia Technologies. It uses the same microprocessor as many 3D printer boards and STM32, but this board is specifically designed for non-3D printer applications in mind, like CNC mills or lathes. What I also really like about this board is that it uses an SPI interface to connect to a Raspberry Pi, which then runs the Linux CNC part. And the board is designed that the Raspberry Pi slots onto it. This setup then gives you quite a compact system with a dedicated machine controller and a dedicated part for the I/O manipulation. And the board is open source. There are a lot more details on this board, which you can find on their Discord or the GitHub page. So for the upgrade of the control system, I got on the one hand the Flexi-HAL CNC board and also a Raspberry Pi 4 in the 4GB configuration. So this is the box. I was wondering about that, but there are enough headers in the packet, as it seems. And then the interesting part, the actual control board. To prepare the setup, first download the pre-configured FlexiPi Linux CNC image, and then use the Raspberry Pi imager or your preferred tool to write the image on an SD card. Insert the SD card and power up the Raspberry Pi. Ensure it boots correctly, and with this the Raspberry Pi setup is complete. Now power down the Pi and connect the Flexi-HAL board. On next startup, the STM32 will also receive power this way. Now we can flash the Remora firmware to the STM32. Run the flash flexi script pointing to the path you can find in the README on the desktop. This version of Remora also has the correct pin layout for the Flexi-HAL, so no changes are needed. After flashing, power off the Raspberry Pi and restart it. Now we can check and load the sample configurations. You can also download or clone more or up-to-date sample configurations from the GitHub. With this we can verify that the sample config loads correctly. I will be using the Access interface as I'm quite familiar with it. Before I put the board in the enclosure, I want to run some tests. So I currently have the board and the Raspberry Pi set up here. It's powered by a variable power supply and it's connected to this oversized monitor. The first test that I did is see if the HAL configuration shows the SPI interface, and I found out that sometimes it doesn't show immediately when you start Linux CNC. You have to take the machine out of emergency once and then it shows up. The next things I want to test is the basic input limit switches. For that I will set up the X, Y and Z limit in the HAL configuration viewer. And then all of these show the corresponding signal. Very nice. After a lot more trial and error than I thought, now also the stepper motor is running. It took a bit longer because at the end I had to flip all the positive and negatives as far as I understood them going out from the Flexi-HAL to my motor controller, and that seemed sort of counterintuitive, so I tried everything else because I didn't want to break anything. Yeah, but in the end I looked at the voltages and this was the only sort of direction that it made sense. So after testing the inputs, the motor drivers and off camera also the spindle, I know how to connect everything and that it works. I did this primarily not to have to do a bunch of troubleshooting when everything is already inside of the cabinet and connected. I put some starting values in the config files, but I will do the actual tuning and configuration when the cabinet is then back on the CNC. To get there I did a bit of cleanup and removed everything that I won't need anymore, and now have started to mock up how I want to configure things. Next then is to prepare some cables, connectors, add some fans, and then start putting it back together. I will start with the high voltage 230 AC side. Everything is connected except the 24 and 12 volt power supply, so I will start with that. Next then is to test that everything turns on and behaves as it should. Okay, we have power to 12 volt, 24 volt, the motor driver as well as the VFD. Looks like everything works, so I will turn it back off and then wait a couple minutes for everything to slowly decharge. The plan is to continue with the 24 volt and then finally do the 12 volt side, just going from highest voltage to lowest. So that was the 24 volt stuff. The only reason I have a connector here, and I don't know if that will be final how it is right now, is so I can disconnect the cables out of the control cabinet, because it's soldered otherwise on both ends and I didn't really like that. The other place it's just the Flexi-HAL that gets 24 volt and that's about it. So I will continue with 12 volt. With the 12 volt, all the power routing should be done. For the lower current 12 volt connections, I've used a sort of bus bar. The only thing I've plugged directly into the power supply is the pump. Sadly, I don't have any other color of cables, so both the 24 volt and the 12 volts are the same color, which will be a struggle to troubleshoot, but hey, that's things. Otherwise everything worked. I am using a 12 volt to USB sort of adapter to power the USB-C side of things, and this one has not found his just there. To connect the signal wires, I will start with the motor cables. Next then is to connect the spindle. I'll control the spindle with the analog 0 to 10 volt output from the controller, as well as a relay to connect forward to ground, to common ground, to turn the spindle on. This was the spindle enable or forward. I still have the manual bypass on the door. I will put the cables just in the enclosure and then we'll do all the cleanup later. Next in are the inputs, and I will start with the end stops. All end stops share common ground up into the machine, so that's why I only have 4 wires, so one common ground and then for all 3 axes each one. Next then is the E-stop or halt switch. Next one will be the tool setting probe to get the tool height. And lastly, something I haven't implemented yet, but I will hopefully do soon, is a touch probe. And with this, everything should be connected. Right now it's just an unholy mess of cables. Originally there wasn't enough space to fit cable trays. With the new setup I could maybe fit them, but I didn't account for it, so I will just use a bunch of zip ties and other cable management tools to hopefully just clean it up. So this is the state. I will probably leave it for now. It's a bit better, not final, but I want to test all the functions on the machine itself before sort of fixing most of it permanently into place. So with all the components in the cabinet, it's time to put it on the machine and do the configuration. The configuration itself is done in the .hal and .ini file. I modified the .hal file for my spindle setup as I use the 0 to 10 volt output, as well as in the axis configuration, as mine is a simple XYZ machine and their moving gantry is, for example, an XYZY. And the .ini are then the limits and measures of the machine itself. Here I started with the pre-installed sample config and used my old step config file as a guide. I will also put the finished files on my GitHub as a reference. The first thing I did to check that the controller and the CNC itself are talking the same language is checking the motors. With the X, Y, and Z positive direction, I had to switch the polarity of all motors as I had them inverted. Next are then the limit switches and the homing sequence. These are under the moving axis and are simple contacting switches now in the normally open position. I don't have any limit switches, so to speak, so I'm relying on the software limits for safety. These are set in the ini file. Here are the software limits as part of the axis limits, and here is the homing sensor position and its sequence. For testing, the additional contactor to only turn off and on the motor driver power supply really came in handy, as I didn't have to unplug any wires. After a bit trial and error, I got the homing sequence to work. Here the 3D printed switch standoffs were quite nice, as they just gave way and are easily fixed with a soldering iron. Next is the spindle control. The 0 to 10 volt output worked right away. I had to include a relay. I tried it without an additional relay, as both the relay driver on the Flexi-HAL and the VFD work on 24 volt, but in the end including one was just easier. Last is the tool height setter. Here I was surprised and elated that the old script that I used just worked with the new setup. It's a measuring macro I got from the YouTube channel Tala83. The only thing I had to change is include a G0 command when moving in absolute coordinates, and I think this is caused by updating the Linux CNC version. With this, all functions I need to run a program are working. As said, I used the step-config file as a base for my motor configuration. These values in terms of speed and acceleration were somewhat limited as I didn't use a modern and or powerful PC in the old Breakoutboard system. So I want to see if I can improve the overall speed and the acceleration with the new controller. I called this configuration tuning before, which is not really correct as I'm using stepper motors and their open loop. There is some tuning in the control loop for the step generation. Here I will stick, however, to my starting values, and if I change anything or find a better setup, I will do an update video. As I don't really have feedback from the motor drivers or the motor itself, I did some guesstimation to find the absolute maximum in terms of speed and acceleration. So as a target absolute speed, I would like something between 2 and 3 meters a minute, which would be 33 or in maximum case 50 millimeters a second in machine units. On my setup with an 1.8 degree stepper, an 8 by microstepping setting, as well as a 3-to-1 reduction between the motor and the lead screw, which also has a 5 mil pitch, I get the 960 steps per millimeter, which is also the scale that I put in the ini file. Running with this scale and going 50 millimeters a second results in needing 84,000 steps per second or running at 84 kilohertz. This is well within the limit of the driver, which can go between 0 and 200 kilohertz. And I also don't think for the Flexi-HAL this is an issue. But for me, speed is another thing if I don't get good acceleration. As I don't plan to do large parts or something in a couple centimeter range, maybe a lower overall speed but a higher acceleration would benefit me more, as the distance traveled is the area under this curve for the velocity over time. The lead to pitch and reduction results in quite a high motor RPM. If I want to go at the 2 meters a minute, the motor needs to do 1200 revolutions a minute. At this point, the torque of a stepper motor is quite low, really depending also on the driver. This torque is then what also limits the acceleration. For the acceleration, I did some trial and error tests to see how high I can go, and now feel quite comfortable with around 1250 millimeters per second squared, which seems to be no issues, and the feed rate here is set to 1500 millimeters per second. This is the most I would feel comfortable right now doing an actual cutting sequence. Maybe if I know the program well enough, I will override it a bit closer to the 2000 millimeters per second. This would mean an increase of both acceleration and normal feed rate of about 200%. After a bit of air cutting, I then milled some parts to see if it works with these values during the actual operation. So this is the part that I just machined, and it's sacrificial backplate for fixturing. I think it came out quite well. Now to see if sort of the settings for the axis are somewhat accurate. It should be 85, and it is. It's almost 85 exact, at least as far as I can measure. Let's see the step. Should be 70, and that's pretty bang on 70. Let's check. That also looks really good. Other axes, so that would be now the y-axis. It is slightly over, it should be 65, and it's 65.3 millimeter, I would say. Let's see, here on the smaller, should be 60, and it's also 60.3, but also 0.3. Sort of these measurements show that the x-axis is pretty spot on, but the y-axis is somewhere plus 0.3 millimeters. I think best thing would be to check the axis first if something got loose or is not as tight as it should be, and then maybe include some backlash, but I'm not really sure. After a couple more test pieces, I can say it's not just the y-axis, but the overplay within the machine. I think this is also caused by the spindle only being connected to the rest of the machine by the one clamp. I can usually get it better than the 0.3 mil. I think 0.2, even 0.1 is doable if I include 1 or 2 spring passes, so overall quite well. The controller is working nicely, and I haven't had any issues and or interrupts during normal operation. And at this point, I feel comfortable enough to leave the machine and not always have my finger over the hold button. Cost-wise for me, it was 125 euros for the board, as I got it shipped from Canada, and this is including shipping and taxes. So I believe it's around 30 to 40 euros cheaper than an entry-level Mesa card. Including the Pi, depending on what prices you get, I think the entire setup is something around 170, 180 euros. The install went somewhat smoothly and was only limited by my lack of knowledge. And I think this is the only drawback from this style of setup, as less people have used it, so there is fewer information just floating around there. But every time I had an issue, the Expartia Technologies Discord was really helpful and got me going again. So big thanks to them. This then marks the conclusion of the bigger issues I had with the machine, and I have now started to machine the parts for the next project, which I also want to document here. See you in the next one.